Hello, everybody. We are Kimberly and Macallister, and today we are going to present to you our project, Methods Behind Elemental Discovery with a specific focus on radioactivity. To start off this presentation, we'd like to give you guys just some background knowledge that scientists had at the time. And a lot of this work was started off by this really good scientist over here, Henri Becquerel. And his early work was concerned with the plane polarization of light with the concept of phosphorescence and absorption of light by crystals. After the discovery of X-rays, accompanied by phosphorescence in a vacuum tube, seen over here in Crookes tube, he decided to investigate whether there was any connection between X-rays and naturally occurring phosphorescence. And to do this, he used his father's uranium salts, which, when exposed to light, would phosphoresce. When the salts were placed near a photographic plate with opaque paper, the plate fogged up. And as you can see by this image here, Becquerel's discovery from salt experiments. And this property was actually found in all uranium salts and characteristic of the uranium atom. And he later proved that these rays differed from X-rays and that they could be deflected by electric or magnetic fields. And as we'll tell you later on, he was awarded half of the Nobel Prize for this discovery of spontaneous radioactivity. Moving on, the Curies were actually very inspired by this work. So Pierre Curie, he was a little bit older than Marie, so he kind of had a little bit of a head start. And he was a French physicist who in 1880, along with his brother, demonstrated that an electric potential was generated when crystals were compressed, i.e. the concept of piezoelectricity, which is used today in a lot of piezoelectric sensors. And Marie Curie had a really cool connection to this because she was a French physicist and chemist. And when she began her scientific career in Paris, she wanted to investigate the magnetic properties of various steels. So that was kind of her connection with Pierre. Now, she was also inspired by Becquerel's discoveries and was looking into uranium rays as a possible field to study for her PhD thesis. Now, Pierre and his brother, 15 years prior to when Marie started, had actually developed an electrometer. And using this electrometer, she hypothesized that radiation was not the outcome of some interaction of molecules, but it must come from the atom itself. And to study this, she focused on two minerals, pitchblende and turbinyle, which is known today as chalcolite. However, she decided to focus more on pitchblende because the electrometer read that it was 4 times more active than uranium itself.
So talking a little bit more about pitch blend, as Max said, they found that this was 4 times more radioactive than any of the uranium oxides or even the thorium oxides that Marie had worked with previously. Um, from this, she was able to form a pretty accurate hypothesis that A, there must be some amount of another radioactive element that was present and was in small enough concentration to previously be overlooked. It had not been isolated yet. B, the unknown element must be significantly more radioactive than uranium in order to be observed in such small quantities so strongly.
The work by all three of these phenomenal scientists led to them being awarded the Nobel Prize in 1903 for physics. And the Nobel Prize in physics for in the year 1903 was divided, one half awarded to Antoine Henri Becquerel in recognition of the extraordinary services he has rendered by his discovery of spontaneous radioactivity, and the other half jointly to Pierre Curie and Marie Curie in recognition of the extraordinary services they have rendered by their joint researches on the radiation phenomena discovered by Professor Henri Becquerel. Now, we wanted to give you just a brief overview of the Curie's work towards this discovery. So, it started off with Marie Curie's thesis research on the analysis of uranium for radiation based off of Becquerel's discovery of radioactivity in 1896, followed by Marie Curie later switching to pitchblende, noting the higher probability of other elements besides uranium being present because it was 4 times more active. And then this eventually led to Marie and Pierre Curie successfully isolating and studying the physical properties of polonium in 1898 and radium in 1902. And a really big takeaway from this is the fact that Marie Curie's work led to the term radioactivity being used to describe the phenomena surrounding these elements/substances.
So a little bit more about radioactivity, which I'm sure many are familiar with, at least vaguely. Initially, the name for these emissions were Becquerel rays after their discoverer, and they were thought to behave very similarly to X-rays. Radioactivity, by definition, is the emission of ionizing radiation caused by a disintegrating atomic nuclei. It's measured by activity of radiation, which is the change in number of particles over time. Um, and the initial nuclei is called the parent nucleus, which then emits one of three types of decay, alpha, beta, or gamma, and is then transformed into the daughter nucleus. Today, we measure these using two different units primarily. The first is the becquerel. This is the international and SI unit, and is recorded in decay per second. There's also the Curie, which is the customary unit, and is the number of decay events per gram of radium per second. And this is a very large number, so typically it will instead be reported in picocuries. On the types of decay, as I said, there are the three, alpha, beta, and gamma. Alpha decay, most are probably pretty familiar with. It's the emission of an alpha particle, and can be easily stopped due to its slow velocity and larger mass. Beta decay is a little bit stronger when it comes to passing through objects due to a higher velocity and lower mass, and is negatively charged, while an alpha decay is positively charged. Both of these tend to exhibit the particle behavior, while gamma decay typically exhibits wave-like behavior, and is the emission of a photon rather than a subatomic particle. One of the key ways that we quantize radiation is by looking at the element's half-life. This is the amount of time that a radioactive isotope will decrease by half of its radioactive nuclei. Um, each radioactive isotope additionally has a characteristic half-life that is directly proportional to the intensity of its radiation. Here we can see the uranium series, which shows the transformation from uranium all the way to lead-206, which is a stable isotope and non-radioactive. As we can see, there are several elements that become the daughter nuclei here. And the half-lives can range anywhere from femtoseconds all the way up to thousands of years.
Now, Marie Curie in the year of 1911 was awarded the Nobel Prize in recognition of her services to the advancement of chemistry by the discovery of the elements radium and polonium, by the isolation of radium, and the study of the nature and compounds of this remarkable element. And a really cool fact to note is that she was the first person to win or share two Nobel Prizes and remains alone with Linus Pauling as Nobel laureates in two fields each, which is a really cool distinction.
So when it comes to observing radioactive decay, initially with these uranium salts, as we kind of said before, in 1896, Becquerel was the first to observe and understand kind of what was happening here. He set out to transform photographic plates using uranium salts over a opaque piece of paper. He would then irradiate this with sunlight and note any relationship between phosphorescence compared to X-ray emission that had been recently discovered. However, on a cloudy day in Paris with no sunlight, he decided to put his experiment into a desk drawer and close it. In the absence of light, the photographic plates still became etched from radiation given off by these uranium salts. This kind of kicked off a fascination with radioactive emissions. Um, Just a few years later, Marie Curie begins making large advances in this area, again, coining the term radioactive. And she does this by measuring the conductivity of air that is caused by decay events, and is able to observe the rate at which an electroscope was charged and discharged from the sample. She determined that the rays that were being observed were actually a property of the element itself, and were consistent across many different types of studies, and somehow left the nuclei seemingly unchanged. She would later go on to say that because of mass balance, there's no way that it was really unchanged, but rather was changing the nuclei so slowly that we couldn't observe it in real time. This would become the half-life phenomenon that I spoke about earlier.
Now, a really key, I guess, substance that was very important to this work was pitchblende. And pitchblende was a vague term for any darker black mineral that had a very high specific gravity in the late 1800s to early 1900s. This term is generally no longer used. And the pitchblende the Curies worked with would be most similar to uraninite, which has an ideal formula of UO2. And the varying stages of radioactive decay and impurities cause deviations in the composition of uraninite. And these impurities are what led to the discovery of new radioactive elements such as radium, polonium, and actinium. The extraction and identification of these elements would take years and have a lasting impact on both the Curies' health and science as a whole.
The path to isolating these elements was, as Max said, very long. Polonium was observed first. However, Marie was never able to fully isolate it from bismuth. She could get a mixture of bismuth and polonium salt, but nothing beyond that. Radium, on the other hand, she was able to eventually isolate in salt form. This began with the observation of both within pitchblende, which then moved into looking at different spectral emissions and identifying that there was, in fact, an unknown present. From here, she was able to dissolve raw ore and break it down so she could then conduct different recrystallizations. The Curies on their own processed 50 kilograms of raw pitchblende, um, with very little return of radium chloride. So what they were able to do was get some assistance from a French factory and were able to process 7 tons of material and eventually isolate 1 decigram of radium chloride that they could then use for further characterizations and studying of radioactivity. One of the key factors in identifying both polonium and radium was the spectroscope. With the help of known spectroscopist Marquet, they were able to identify unique emission bands in the spectra from the radiation emissions. Spectroscopes are still used today, and one of the most well-known applications is in the hydrogen spectral series. If you've ever heard of the Lyman, Balmer, Passion, there's many more. Any of the series, they're what allow us to quantize energy transitions based on light emissions. And this was very key in identifying these elements. Another large contributor to this discovery was the electroscope, which the most common version at the time was the gold leaf varietal, where there's a brass cap on the top of the apparatus where you load your sample. And depending on the charge of the system as well as the charge of the sample, the gold leaves in the center would either converge or diverge, to indicate the flow of charge. From this, the Curies were able to test numerous minerals and elements, and determine the ranking of radiation that was coming off of them. And this is how they were able to determine, A, that raw pitchblende was more radioactive than uranium, but also then that radium itself was so radioactive.
The last important tool that was helpful in this scientific work was the parallel plate apparatus, or as it's known today, a parallel plate capacitor. And parallel plate capacitors are formed by an arrangement of electrodes and insulating material or dielectric. A parallel plate capacitor can only store a finite amount of energy before dielectric breakdown occurs, and it is typically defined as when two parallel plates are connected across a battery, the plates are charged and an electric field is established between them. Lastly, we would like to end by just discussing the impact of the Curie's work. So, in the 20th century, it had a large variety of applications, such as medical applications. So, as you can see, in World War I, Marie Curie, with her daughter, actually utilized these petite curies, which were little mobile X-ray units that they used on the battlefield and saved thousands of soldiers' lives by identifying their wounds. Right next to this image, you can see these little needles, and those are actually radium needles, and they inserted them into tumors to help shrink them. Um, Next, people back in the day, in the early 1900s, did not know how toxic radioactive substances were. They actually thought the opposite. They thought they were very beneficial, so they used to put it in their food. It was found in things such as chocolate and even toothpaste. And then it was also used in consumer products. So as you can see, they used it for watches, plane gauges, anything to make it light up and glow. And then polonium was used as an atomic heat source. It's still used as an atomic heat source today. It was used, I think, in the 1950s or 60s for spark plugs for cars to help start the engine. And lastly, it used to be used in a lot of complex static reducing tools. So, really cool applications. Lastly, the Curie's work in the 21st century, so modern day, it actually is still very beneficial, such as through the use of radio tracers. So, technetium is a very important one, which is used to image damaged heart, liver, and lung tissue. Thallium 201, which becomes concentrated in healthy heart tissue. So, typically, thallium and technetium are used hand in hand to help diagnose any heart related issues. Iodine 131, it concentrates in the thyroid gland, liver, and some parts of the brain, and it's used primarily to monitor Graves' disease, as well as sodium 24, which helps locate obstructions to the flow of blood, and it's usually administered like through a salt solution. And this last one that we want to point out is the samarium 241. While it's not a radio tracer, it's actually used in smoke detectors. So you have this really cool element. We should all have them in our homes. So pretty cool work. And the work that the Curies did has been very important. It was pivotal in the 20th century, and it continues on into the 21st century. And we were just both really inspired by Marie Curie, and we hope you enjoyed this presentation. Thank you.